Assalamu alaikum students. Today we will discuss about the heat treatment processes. Engi- Heat treatment processes. Engineering materials are used for various applications. For example, there are more than 2000 types of steels, more than 5000 types of plastics, and there are more than 9000 types of aluminum alloys, and there are more than 10,000 types of glass. So heat treatment process is required to improve the or to enhance their mechanical properties for the steels, plastics, aluminum alloys, and glass. What is heat treatment? Heat treatment can be defined as a combination of heating and cooling operations carried out on a metal or alloy in a solid state so as to produce a particular microstructure and hence the desired properties. Generally, the composition is fixed and the solidification is also completed. The only way to change the properties is by heat treatment. Heat treatment effectively alters the size and shape of the grains and also the type of the structures SCC, BCC, FCC, HCP structures, etc. And the distribution of grains. Hence, all the treatment is effectively used to change the size and shape and the properties of a material, whether it is a metal or alloy in a solid state. Heat treatment process is a series of operations involving the heating and cooling of metals in a solid state. Its purpose is to change the mechanical property or combination of mechanical properties so that the metal can be more useful, serviceable, and safe for definite purpose. By heat treating, a metal can be made harder, stronger, and more resistant to impact. Heat treatment can also make a metal softer and more ductile. Types of heat treatment processes. There are about 7 types of heat treatment processes. The first one is case hardening. Case hardening involves an intentional build up or addition of a new layer with increase in part dimensions. Its parts are it can be divided into subparts. The one is carbonizing, where are some carbonizing can also be divided into its subparts: pack carbonizing, gas carbonizing, and liquid carbonizing. The second type of case hardening is cyaniding, nit-riding, carbonitriding. The second type of case hardening is surface hardening. Surface hardening. Surface or subsurface modification without any intentional build up or increase in the part dimensions. Its types are flame hardening, induction hardening. All the above discussed classification of heat treatment processes are basically for ferrous metals. Types of heat treatment processes. There are different types of heat treatment processes. So far we have discussed in previous slides, and in current slide we are discussing the summary of the heat treatment processes, one of which is annealing. Annealing was subdivided into three more parts, like stress relief annealing, full annealing, like that. We will discuss it, all of these types of heat treatment processes one by one. Second one is normalizing, and then hardening, quenching, carbonizing, Nit-riding, and some other types of heat treatment processes. We will discuss these in this lecture. Material selection. The materials are selected on the basis of performance, availability, and cost. Performance of a material depends on its properties, while properties in turn depends on the internal structure. Performance depends upon the properties, properties depends upon the structure. The structure depends upon the solidification, the composition, the heat treatment. If we do well heat treatment for a specific alloy or metal, the structure can be perfect, or the properties of the structure can be enhanced. Or if we select if we manufacture type of steel, where by changing the composition of an alloy, a structure can the structure of that alloy can be or the properties of that alloy can be enhanced. Similarly, the solidification process also depends upon the building of a structure, the enhancement of the structure. Objectives of the heat treatment. The primary objective of the heat treatment is to improve the mechanical properties, to improve the machinability, to increase the wear resistance, to modify the electrical and magnetic properties, to refine the grains, to produce hard surfaces and soft inner core. So one of the part of the heat treatment is annealing. What is annealing? Annealing involves heating the material to a predefined temperature and hold the material at temperature and cool the material to the room temperature or in an oven slowly. The process involves the heating of a material at the elevated predefined temperature, holding the material, we call it soaking, at the temperature for longer time. Usually we do it in the oven. Very slowly cooling the material to the room temperature. The annealing process consists of heating the steel to or near the critical temperature. Critical temperature we have defined as before. It is the temperature at which crystalline phase change occurs. Sometimes we call it, for the binary eutectic phase diagram, we call it eutectic temperature or isothermal temperature. We do it to make it suitable for fabrication. When annealing part is allowed to cool in the furnace, it is called full annealing or full anneal hot heat treatment. The various purpose of these heat treatment in the annealing is to relieve the internal stresses developed during solidification. Then there are some internal stresses that are developed during the solidification. So annealing is one of the heat treatment process to relieve the internal stresses, or and to relieve the internal stresses developed during the solidification in machining, forging, rolling, or welding to make our material better for machining, forging, rolling, or weld. To improve or restore ductility and toughness, to enhance machinability, to eliminate chemical non-uniformity, to refrain grain size, and to reduce the gaseous contents in the steel which were formed during the manufacturing from the cast iron to steel by adding the different compositions of carbon and another alloys. How to differentiate between annealed metals and hardened metals? As we have studied, in annealed metals, usually the internal stresses are relieved to make the core softer, while so in annealed metals the ductility is improved. Annealed metals are usually ductile, while what is the difference between the hardened metals? Hardened metals in which the ductility is reduced, the brittleness is increased. Hardened metals are more brittle, while annealed metals are more ductile. Annealed metals, in annealed metals, the ductility can be improved, or in elongation there must be some elongation due to the stresses which were relieved, the elongation is produced. So if we apply a force, elongation is produced. In hardened metals, if we apply force, the hardness is increased, although, but the ductility is reduced. The material can be broken at the end of at the middle of the where force is applied. Annealing range. In this figure we can find out the range of annealing process. The yellow region is austenite. This is the region for austenite. When a material is cooled down from a temperature from melting point, and if we cool down from say from 1000 degrees centigrade to suppose over here, if we cool down this material to 1000 degrees centigrade, this one is the range of normalizing. This curve shows the normalizing range, while this curve, this region, shows the ferrite and austenite, while this curve, this region, is ferrite plus austenite region. Over here, the horizontal axis, it shows composition of carbon by weight. Over here, the less than 0.8% is the range for the hypoeutectoid steel, while if we cool down beyond 0.8%, cementite and perlite region is here. Where is the range for the full annealing? If we cool down a metal from its melting state, say about less than 10,000 10,000 degrees centigrade, and if we cross the normalizing range, if we cool down over here to a temperature about less than 800 degrees centigrade, we can solidify the material at this given temperature within the oven for in order to get the full annealed range. This is the full annealed range, which is starting from below 800 degrees centigrade and above 750 degrees centigrade. This is full annealing range. While if we cool down the material below this 750 degrees centigrade, we can get a material cool down within a process annealed range. Calculation of tensile strength of annealed hypoeutectoid steels. The approximate tensile strength may be determined by the proportions of ferrite and perlite present in that alloy. The general formula for the approximate calculation of approximate tensile strength for the alloys with the ferrite and perlite percentages is the approximate tensile strength is equal to 40,000 multiplied by percentage of ferrite plus 120,000, which is psi, multiplied by percentage of perlite divided by 100. For example, an annealed 0.20% carbon steel contains approximately 25% perlite and 75% ferrite. Apply the above formula. The approximate tensile strength is equal to 40,000 multiplied by this 75%, which is 0.75, plus 120,000 multiplied by 25%, which is this 0.25, divided by 100. We have already divided 75% is equal to 0.75, 25% is 0.25, which is equal to 60,000 psi. Here we want to mention that the same idea cannot be applied to hypereutectoid steels. This is for hypoeutectoid steels because the strength is determined by the cementite network, which forms the continuous phase. The presence of the brittle network results in a drop in tensile strength. Spherodizing. Spherodizing is another method of heat treatment process. In an annealed hypoeutectoid steel with a microstructure of perlite and cementite network will give poor machinability. Since cementite is hard and brittle, the cutting tool cannot cut through these plates. A heat treatment process which improves machinability is known as spherodized annealing. Method for spherodized heat treatment. Three steps are used for the spherodized heat treatment. Prolong holding at a temperature just below the lower critical line. Heating and cooling alternatively. Heating and cooling alternately between temperatures that are just above and just below the lower critical line. Heating to a temperature above the lower critical line and then either cooling very slowly in the furnace or holding it at a temperature just below the lower critical line. The prolonged time at elevated temperature will completely break up the perlite structure and cementite network. The spheroidized structure is desirable when minimum hardness and maximum ductility, or in case of high carbon steel, maximum machinability is important. Low carbon steels are seldom spheroidized for machining because in spheroidized condition they are excessively soft and gummy. The cutting tool will tend to push the material rather than cut it, causing excessive heat and wear on the cutting tip. Medium carbon steels are sometimes spheroidized annealed to obtain maximum ductility for certain working operations. In this figure, the mechanical properties of normalized and annealed steel are mentioned over here. In the first column, carbon percentage composition is mentioned. Yield point is mentioned in the second column. The tensile strength is mentioned over here, and elongation of that particular material, and then reduction in area and Brenner hardness test is given in this table. For carbon percentage composition with the 0.01 carbon percentage composition, the yield point is this much multiplied by 1000 psi, while the tensile strength is this much multiplied by 10,000 psi. The elongation is this much. If we this is the procedure for the normalized heat treatment, while for the annealed heat treatment, the procedure the table for the annealed heat treatment with the carbon composition with the same carbon composition, if we compare both the same compositions for the mechanical properties, over here in this case the yield point is 18,000 psi, while in case of normalized the yield stress is increased. Over here for the same composition, the yield tensile strength is 41 multiplied by 1000 psi, while this has been improved for the normalized. Same results can be achieved. A relatively improved and hardened structure is achieved in normalized heat treatment. Stress relief annealing. Uh, this process, sometimes called subcritical annealing, is useful in removing residual stresses due to heavy machining or other cold working processes. It is usually carried out at a temperature below the lower critical temperature line, which is usually between 100 to 1000 to 1200 degree Fahrenheit. No microstructural changes occur during this process, during the process of stress annealing. Only the internal stresses which were developed are relieved in this stress relief annealing. Internal stresses are those stresses which can exist within a body in the absence of external forces. These are also known as residual stresses, or locked in stresses. These stresses are developed in operations like solidification of castings, welding, machining, grinding, short peening, uh, surface hammering, cold working, case hardening, electroplated coatings, precipitation, and phase transformation. Stress relieving. These internal stresses which were developed in the structures, these internal stresses under certain conditions can have adverse effects. For example, steel with residual stresses under corrosive environment fail with the stress corrosion cracking. The stresses also enhance the tendency of steels towards rappage and dimensional instability. Fatigue strength is reduced. Fatigue strength is reduced, and when reduced considerably when residual tensile stresses are present in the steel. The problem associated with internal stresses are more difficult in brittle materials than in ductile materials. This is one of the example of the internal stress which was generated inside the structure. Due to this internal stress, corrosion occurred in the cracks was further generated inside the structure. Process annealing. The heat treatment is used. Heat treatment is used in the sheet and wire industries, and is carried out by heating the steel to a temperature below the lower critical line, which is 1000 to 1200 or 1250 degree Fahrenheit. It is applied after cold working and softens the steel by recrystallization of further working. It is very similar to stress relief annealing. Parts which are fabricated by the cold forming, such as stamping, extrusion, offsetting, drying, are frequently given. This treatment is an intermediate step. Scaling or oxidation can be prevented or minimized by this process, especially if annealed at lower temperature or in non-oxidizing areas. This is the range for different types of annealing, the heat treatment processes, the range of different types of heat treatment processes. This is the range on of temperatures of normalizing, while this is area of the full annealing range. The full annealing range is between 1000 to 1200. The process annealing range is between uh, starting from 1250 degrees centigrade to 1350 degree Fahrenheit. Similarly, the full anneal this is the full annealing range, and when a metal is cooled down from austenite region, then what type of structures are made at what temperature, this is mentioned, and over here the carbon percentage is composition is shown to differentiate between the different types of microstructure like perlite and ferrite. The percentages, one is for the hypoeutectoid steel, the other is for hypereutectoid steel. The uh, the microstructure, which is cementite plus ferrite, is in the range from 1000 to 1200 degree Fahrenheit. Normalizing, it's a different type of heat treatment process. The purpose of normalizing is to produce a harder and stronger steel than full annealing. Actually, we can produce harder and stronger steel. We can fabricate harder and stronger steel in normalizing as compared to full annealing. So that for some applications, normalizing may be a final heat treatment. Therefore, for hypereutectide steels, it is necessary to heat above the ACM line in order to dissolve the cementite network. Normalizing may also be used to improve the machinability, modify and refine cost dendritic structures, and refine the grain and homogenize the microstructure in order to improve the response and hardening operations. The increase in cooling rate due to air cooling is compared with furnace cooling affects the transformation of austenite and resultant microstructure in several ways, since we are no longer cooling under equilibrium conditions. This is the ACM line for the normalizing. The normalizing consists of heat steel to about 40 to 45 degree centigrade, 40 to 45 degrees centigrade above critical temperature. This much above critical temperature. Suppose if this is the critical temperature line, then add 40 to 45 degrees centigrade. Uh, so it will give you the limit for the normalizing. And holding the proper item and then cooling in still air or slightly agitated air to room temperature. The summary of the normalizing is to cool down from material, a steel from austenite region to slightly above 40 to 45 degrees centigrade above the critical temperature, and in the presence of still air or slightly agitated air to room temperature. The comparison of normalizing and annealing. After normalizing, the resultant microstructure should be perlatic. This is the comparison of microstructure between the annealed and normalized. Both are the lamellae structures, the continuous layers, subsequent layers of ferrite and cementite, but medium lamellar perlite in normalized the structure microstructure is medium laminar perlite, while for annealed the microstructure is coarse laminar perlite. Since the temperature involved in this process is more than that for annealing, the homogeneity of austenite increases. As a result, better dispersion of ferrite and cementite in the final structure can be observed. Result in better dispersion of the ferrite and cementite in the final structure. The grain size is finer in normalized structure than in annealed structure. Normalized steels are generally stronger and harder than fully annealed steels. Uh, the comparison between annealing and normalizing: steels are soft in annealed condition and tend to stick during machining. By normalizing, an optimum combination of strength and softness is achieved, which results in satisfactory level of machinability in steels. Normalizing is effective way to eliminate the carbide network. Normalized treatment is frequently applied to steel in order to achieve any one or more of the objectives, namely to refine the grain structure, to obtain uniform structure, to decrease residual stresses, to improve machinability. While in annealing, the residual stresses can be relieved, or internal stresses which were developed when the structure can be relieved during annealing process, while for the normalizing we can improve the microstructure as well. Just like we have studied the microstructure, we compare the microstructure of normalized and annealed metal. The normalized microstructure is fine, while laminar structure, while for the annealed is a coarse laminar structure. This is the table which shows the optimum microstructure for machining steels of different contents. The carbon percentage is mentioned, and the optimum microstructure which will be formed is shown in this table. This is the percentage of the carbon composition between 0.06 and 0.02. The optimum microstructure will be as cold, just like cold rolled, and the proper heat treatment process is also shown for the percentage wise carbon composition. Hardening. Hardening is a heat treatment process in which the steel is rapidly cooled from austenizing temperature range, which is usually 727 degrees centigrade or above. As a result of hardening, the hardness and wear resistance of steel are improved. Uh, Hardening treatment generally consists of heating to hardening temperature, holding at that temperature, followed by rapid cooling, such as quenching in oil or water or salt baths. This is the figure which shows the hardening range, the normalizing range, full annealing, and hardening range. This is the hardening range. Hardening. The high hardness developed by this process is due to the phase transformation accompanying rapid cooling. The high hardness developed by this process due to the phase transformation accompanying rapid cooling. Rapid cooling results in the transformation of austenite at considerably low temperature into non-equilibrium products. The hardening temperature depends on the chemical composition. For plain carbon steel, it depends on the carbon content alone. Hypoeutectoid steels are heated to about 30 to 50 degrees centigrade above the upper critical temperature, whereas eutectoid and hypereutectoid steels are heated about 30 to 50 degrees centigrade above lower critical temperature. Ferrite and perlite transform to austenite at hardening temperature for hypoeutectoid steel. This austenite transforms to martensite on rapid quenching from hardening temperature. The presence of martensite accounts for high hardness of quench steel. Hardening is applied to cutting tools, machine parts where high hardness and where wear resistance are important. The process variables. The process variables are hardening temperature, soaking time, delay in quenching. The hardening temperature. The steel should be heat treated to optimum austenizing temperature. A lower temperature results lower hardness due to incomplete transformation of austenite. If this temperature is too high, it will also result hardness due to a coarse grain structure. Soaking time. Soaking time at hardening temperature should be long enough to transform homogeneous austenite structure. Soaking time increases with increasing in section thickness and amount of allying the element. Delay in quenching. After soaking, the steel is immediately quenched. Delay in quenching may reduce hardness due to partial transformation of austenite. Type of quenching medium also has profound effect, which will be discussed briefly in the next upcoming slides. The main purpose of hardening tool steel is to develop high hardness. This enables tool steel to cut other elements. High hardness developed by this process also improves wear resistance. Gears, shafts, and bearings. The high hardness developed by this process also improves the wear resistance in gears, shafts, and bearings. Tensile strength and yield strength are improved considerably due to hardening structure steels. Because of rapid cooling, high internal stresses are developed in the hardened steel. Hence, these steels are generally brittle. Hardening in general is followed by another treatment known as tempering, which reduces internal stresses and make the hardened steel relatively stable. Tempering. Hardened steels are so brittle that even a small impact will cause fracture. A small impact will cause fracture. Toughness of such a steel can be improved by tempering. However, there is a small reduction in strength and hardness, which is shown in the attached figure. Tempering is a subcritical heat treatment process used to improve the toughness of hardened steel. Tempering consists of reheating of hardened steel to a temperature below lower critical temperature and is held for a period of time and then slowly cooled in air to room temperature. In the attached figure, in the attached figure, the hardness versus elongation are shown for the uh, different types of materials. At 100 degrees centigrade, the relationship of hardness, toughness, and elongation for materials are shown. At 100 degrees centigrade, the materials have high hardness but lowest elongation. As soon the temperature increasing, the for the heat treatment in the heat treatment process, the elongation increases while the hardness decreases. A point is reached where the material have the lowest hardness, like about less than 55, and the highest the linear relationship of elongation. After that, the linear relationship of elongation is finished, and then elongation decreases and a point is reached where the temperature have the at about 600 degrees centigrade, the elongation is highest while the hardness is at the lowest point. Tempering temperatures are usually identified by the color. The temperatures are related to the function of the parts. Cutting tools are tempered between 230 to 300 degrees centigrade. Cutting tools. If greater ductility and toughness are desired, as in case of shafts and high strength bolts, the steel is tempered in the range of 300 to 600 degrees centigrade. At tempering temperature, carbon atoms diffuses out and fine cementite and sulfur ferrite structure left behind. The carbon atoms diffuses out and fine cementite and sulfur ferrite structure left behind. Thus, the structure of tempered steel consists of ferrite and fine cementite. Depending on temperatures, tempering processes can be classified as low temperature tempering at a temperature range of 150 to 250 degrees centigrade. Medium temperature range, the temperature range is for medium temperature is 350 to 450 degrees centigrade. High tempering temperature, the high tempering temperature range is from 500 to 650 degrees centigrade. These are the types of colors for the steel. The normalized color is this one. For the quenched color is this one. While the range for the 600 to 50 degrees centigrade is the different temperature range for the normalized is this one, while quench colors for the required temperatures are quenched like 400 degree centigrade is this one, degree Fahrenheit, 500 degree Fahrenheit, 590 degree Fahrenheit, 730 degree Fahrenheit. These are the colors for the quenched. Temperatures are usually identified by the color. Temperatures for tools and shaft along with the tempered colors are given in this table. For the pale yellow color represents the temperature of 230 degrees centigrade for lathe tools for brass. Dark yellow, brown, the brown purple, the blue color, the temperature range for the blue color is 300 degrees centigrade for the springs. Attached is one sample example, a sample figure is given for the, and the color has been divided into the sub portion, like for 270 degrees centigrade is the peacock, reddish bronze is 260 degrees centigrade, deep straw is 250 degrees centigrade, and straw for 230 degrees centigrade. Similarly, for cutting tools, if we look at this cutting tool, the color, these are different colors for the tempering temperature range.